let me first give you the following theorem, which is useful in finding Nash solutions. I'll write it in the short form. By the way, when talking about mixed extension games, all the games that we're talking about will be finite games. That is, games where the strategy set of players consists of finite sets. Okay? So, mu is a Nash equilibrium of the mixed extension of gamma if and only if, so for any mu is a Nash equilibrium of the mixed extension game gamma if and only if for any agent I, the following holds. For any Si prime, Si double prime in the support of mu I, the expected utility that agent I gets by playing Si prime, given that the opponent plays according to mu minus I, and the expected utility payoff that player I gets when he plays Si double prime, given that his opponents are playing according to mu minus I, are equal. This is what your friend has just used in the first lecture. Okay, so I will not write the proof, but it's easy. If mu is a Nash solution of the mixed extension game, then mu I is a best response of player I to mu minus I. If mu I is a best response to mu minus I, then anything in the support of mu I is a best response to mu minus I. Well, if those two, if Si prime and Si double prime are best responses to the same strategy of the opponents, they should yield the same expected payoff. And for any Si prime in the support of mu I, and for any Si prime that is not in the support of mu I, the expected payoff that player I will get when he plays, double prime here, when he plays Si prime, given that his opponents are playing according to mu minus I, and the expected payoff that he gets when he plays Si double prime, the opponent's playing mu minus I, should be greater just greater or greater or equal? Okay, so should we put equality? How many vote for inequality? Okay, how many vote for equality? The egalitarians among us. Only one person? Two? So, do you have an example in mind that it should be? You're just in favor of equality. It doesn't matter if you don't play one of them. Exactly. That's kind of a, you see, let's take a simple, I'll write a very simple game. Okay. So, top, bottom, left, right. So, by the way, what did we talk? Any pure strategy Nash equilibria are also mixed strategy Nash equilibria, okay? Well, maybe we'll prove that later on too. I think we didn't prove that, right? We just said it was kind of an obvious, but it again relied on that the expected payoff from a mixed strategy is a convex combination of expected payoffs from pure strategies, okay? So TL is a Nash equilibrium. That is the mixed strategy where T is played with probability 1 and B is played with 0. And L is played with probability 1, R is played with probability 0, is a Nash solution. But what is the expected payoff that player 1 gets when he plays T? It's 1. What is the expected payoff when he plays B? It's again 1. In which case we have equality. Okay. So that's what we have. By the way, the discussions we had actually, supports this direction. So this also follows simply because we said if SI prime is in the support of mu I, we know that SI prime is a best response to mu minus I. So it should yield at least as much expected payoff than any other strategy, mixed or pure, of player I. That's what this says. Okay? So this side is kind of trivial. The interesting part is this side, which is the part that is useful for us, because using these two conditions, we can find Nash solutions. Okay? We'll maybe do the proof of this, but before proving it, let's use it. Actually, I'll try to solve a problem from the book. Just before I came for the lecture, I decided to pick up a problem. I don't know whether it's going to be easy or hard, but we'll give it a try. We'll try it together. So this is exercise 141.1 from Osborne's book, An Introduction to Game Theory. So it gives a game in tabular form. Top, bottom, left, middle. Well, I usually use center, but let's use the notation Osborne used. And the Bernoulli payoffs are those are the Bernoulli payoffs. By the way, from now on, whenever we're given a strategic form game in tabular representation, we take the numbers here as the numbers that are yielded by the Bernoulli utility function. They are the Bernoulli payoffs. So we can find the expected payoff, okay, by using these numbers. Okay? So the question is, find all mixed strategy, it's find all the Nash solutions of the mixed extension of this game. Okay. So what do you do? Well, we can go back to our old method, using the pictures. But let's not do that. Let's try to use these things. Well, the first thing I would do is, first of all, look at the original game. Does it have any Nash solutions, right? So for that, I will mark the best responses. That's B is a best response to L, B is a best response to M, T is a best response to L, M is a best response to T, and also L is a best response to T. And then both L, I'm sorry, well, that's not L, that's right, R. Both L and R are best responses to B. So immediately from this picture, we see that there is two pure strategy Nash equilibria. So the Nash equilibria of this game is, the original game is BL T R. Okay, so the Nash equilibria of the mixed extension game will be, so 0, 1. The first number denotes the probability with which T is played. The second number denotes the probability which B is played. So that's the mixed strategy of player 1. And the mixed strategy of player 2 is 1, 0, 0. So that's one strategy profile. Player 2 plays L with probability 1 and M and R with probability 0. And the other one is 1, 0, 0, 0, 1. Okay. So, by the way, there might be more. That's what we want to find. Okay? Because any Nash equilibria of the original game induces a Nash equilibria for the mixed strategy extension. We already know these. Are there more? And rather than using pictures, we'll use these facts. Okay? So, how do we use that? How do we use these facts? Well, pick a mixed strategy. Pick an agent. Okay. Now, what can happen? For example, for player 1. Only T can be in the support of the mixed strategy of player 1. Only B can be in the support of the mixed strategy of player 1. Both T and B can be in the support of the mixed strategy of player 1. And then for player 2, only T, only M, only R could be in the support. T and M can be in the support. T and R, M and R, okay, and L and R, and then everything. So what we have to do is investigate all these cases. Okay. So at the end, we'll get the answers, but it's going to take a little work. Okay. So let me simplify notation. I don't want to keep writing mu1, mu2 every time. So I'll denote the mixed strategies of player 1 with PT, PB. Mixed strategies of player 2 with Q. So QL, QM, QR. So I don't have to write mu1 in brackets and all that stuff. Okay? So by the way, I just remembered this because of a question one of your friends asked during the break. Remind me after we finish this example to tell you why we use this notation to denote the set of mixed strategies of player 1. Okay, so remind me why we use this notation to denote the set of probability measures on SI. Okay, why put a delta here? Okay. Okay, so be such that. Well, let's start with the following. Actually, Let me erase this part. Okay. So let PQ be a Nash equilibria, okay, of the mixed extension game, be such that PT and PB are both in the support of P. That is, both PT and PB are positive. What does that imply? According to this condition, if PQ is a Nash equilibrium and both PT and PB are in the support, they should yield the same expected payoff. So then U1 of TQ should be equal to U1 of BQ. Okay. What is U1 of TQ? Well, it's 2 times QL plus 0 times QM plus 1 times QR. So 2 times QL plus 0 times QM plus 1 times QR. And what is this? Here we have 3 times QL plus 1 times QM plus 0 times QR. Okay? So far, so good? Nothing fancy. So, one equation, 2 unknowns. By the way, this part is no use for me because everything is in the support, so this condition is no use. So, what would you do next? Okay, right. So we know that these numbers add up to 1, so we can get rid of one of the variables. For example, QR. Okay, so this is going to be 2 times QL plus 1 minus QL minus QM times 1. And here we will have 3QL plus QM. That doesn't really matter. So what do we have? QL minus, well, I'll go slow because I make a lot of arithmetic mistakes. So what does that imply? 2QL is equal to 2QM. That implies QL is equal to QM. Right? Did I make a mistake somewhere? That's minus, that's minus. Where did I make the mistake? That's 1 minus? Uh-huh. Oh, yes, I forgot the 1 here. Sorry, thank you. As I said, I'm very good at making these mistakes. And as I said, if I was a smarter instructor, I would have said I was checking you guys. But that's not definitely the case. So from there, we get 2 QL plus 2 QM. Well, let me simplify this. QL plus QM equal to 1 over 2. Okay? So far, so good? Any questions? Any questions? Okay? By the way, we started by an assumption on the mixed strategy of player 1. We got a condition on the mixed strategy of player 2. Okay? So, If this game has a Nash equilibrium, we know that mixed extension games does have Nash equilibrium. We talked about that the week before the exam. Okay. Then these Nash equilibriums should be such that if player 1 plays T and B with positive probabilities, then QL and QM should be played with in such a way that their probability should add up to 1/2, right? And what does that imply? QR is equal to 1/2, which is positive. Okay. So, what's the next thing to do? Let's do it for the second agent. So, we know that QR is equal to, if this is the, by the way, be careful. If this is the case, then QR has to be equal to 1/2. Okay? So this all started by assuming that both T and P, by the way, that's bad notation, I'm sorry. PT is a number. T and B are in the support of P. Sorry about that. We should use the language properly. Sorry about that. Okay. So if both T and P are in the support of P, then QR has to be equal to 1/2. But QL and QM could be any two numbers, non-negative, which add up to 1/2. So what is the thing that you would do now? Well, again, I'm going to make use of this. Obviously, R is in the support of Q. But then this condition doesn't say anything about L and M being in the support of Q. So we will investigate the cases separately. So which one do you want to start with? Well, let's start with, sorry?
They're both in the support.
They're both in the support. So if L and M, this time I wrote it correctly, in the support of Q, what does that imply? Well, then R, we already know that R is also in the support. So in that case, we have U2 of PL equal to U2 of PM equal to U2 of PR, because we already know that R is also in the support. We didn't have to assume that. Okay. So what does that mean? Well, we'll calculate each of these numbers. So U2 of PL is 2 times PT plus 2 times PB. So that's equal to 2 times PT plus 2 times PB. That has to be equal to 3 times PT plus 1 times PB. What were the numbers? Well, let me keep it like this. P. And that has to be equal to 3 times PT plus 2 times PB. By the way, PT plus PB is equal to 1, so this thing is equal to 2. Again, we know that PT plus PB is equal to 1, so we can write this as, now, well, let me go step by step. So that's 2 PT plus 1. That has to be equal to, again, so that's equal to PT plus 2. So these two implies PT equals to 1/2, right? And these two, wait a minute. That's, what did I do? That's PT, right? Yeah. And this implies PT equals to 0. So all three of them cannot hold at the same time. We arrive to a contradiction. Which means that if T and B are in the support of P, then it cannot be the case that both L and M are in the support of Q. Okay? Okay? So, but they have to add up to 1/2, so it means that only one of them is in the support. So that's what we'll do. That's what we will investigate. So let me erase this part. So we have L in the support of Q. Again, remember R is already in the support. So what does that imply? I'll just use this and this. So that was equal to 2. That's equal to, so 2 equals to, again, I'm just using the numbers here. Then U2 of PL has to be equal to U2 of PR. That is, 2 has to be equal to PT plus 2. And these numbers have to be bigger than U2 of M. So let's, right? So that has to be, and so that's equal to PT plus 1. But this implies PT equal to 0, right? And if I put 0 here, what do we get? 2 is greater or equal to 1. So all is fine. So from this, we get PT equal to 0. We already had PT equal to 0. Okay? So far, so good? Exactly. Remember, where did we get this? How did we get to this point? That was here. I raised it. We arrived here by assuming that T is in the support of P. But we had PT equal to 0, contradicting T in the support of P. So this can't be the case. So this was condition 2. This can't be the case. We already showed that this can't be the case. Then we'll look at condition 3. M is in the support of Q. In that case, let me again write it. U2 of PM is equal to U2 of PR, which is greater or equal to U2 of PL. So this number was 2 PT plus 1. This number was PT plus 1. And this number is equal to 2. So for this to be greater or equal to 2, PT has to be equal to 1, right? Because that's a probability. So this implies PT equals to 1. But if PT is equal to 1, sorry? Well, even before that, these two equalities, actually even, did I make a mistake there again? Oh, this is 2. I'm sorry. Sorry. So again, let's back up. Sorry about that. So I thought it was a 1. I was looking at this. That's what I should have looked. Okay. So let's use this side. What does that say? Move that here. PT equals to? Oh, okay. So PT equals to 1. And that's in accord with this. There's no problem there. Okay? So PT equals to 1 implies PB equal to 0. But that contradicts with? Contradicts with B in the support of P. Okay? So far, so good? Okay? So, what's the conclusion?
T and P cannot be in the support.
Exactly. Both P and T cannot be in the support of a mixed strategy of player one's strategy, mixed strategy, which is a part of a Nash equilibria of the mixed extension game. Okay, they both cannot be in the support. So then what do we do? Take it one by one. Okay, only T is in the support. If only T is in the support, then what do we do? Okay. Then you look at the mix. Well, let's write it down. We have still time. So conclusion here, if PQ is a Nash solution of the game gamma, then support of P is not equal to TB. Okay? So then we go, assume support of P consists of only T. Okay? Okay? Then, again, what do? We look. The support of Q. Can it only consist of L? No, right? Because if he plays L, his expected payoff is going to be 2. But if he plays any mixed strategy which places a positive weight on M or R, it would yield, well, even with, we don't have to look at the mixed strategy. If L is in the support of Q, then the expected utility that he gets by playing L should be greater than or equal to the expected utility that he gets from any pure strategy. That's not the case. So L cannot be in the support of Q. Can M and R be in the support of Q? Yes, right? Okay. So I will not write those parts, but from here we see that actually if the expected payoff that he gets by playing M is equal to the expected payoff that he gets by playing R, given that player 1 is playing T with probability 1. Okay? And the expected payoff that he gets from playing those two pure strategies is bigger than the expected payoff that he gets by playing L. Which gives us any strategy profile of this form where PM plus P, not P, those were Q. I'm getting tired. QM, QR equals to 1 is a Nash solution of the mixed extension game. And then we go, assume support of P is equal to B. That is, he plays B with probability 1 and T with probability 0, which means that we restrict our attention to this part of the table. And what do you think happens here? He plays L and R with any probability, and M with probability 0. That is, L and R on the support, but M is not. So I'll write the conclusion. Okay. I'll write the conclusion in the following form. It's 1, 0, 0, QM, QR. So strategy profiles of this form, where QM, QR are non-negative, and QM plus QR is equal to 1. Okay. Union, by the way, QM can also be equal to 0 if M is the only, so if player 1 plays T with probability 1, and M is the only, can M be the only element in the support of Q? Well, yes, M is in the support, so it means that the expected payoff that he gets by playing M should be at least as much as the expected payoff that he gets by playing any other pure strategy. If he plays R, it's 3 equal. If he plays L, it's 2 less. So this condition still holds. Okay? There's a mistake there. I did talk too fast. I did talk so there's a mistake that I made. What's the mistake? What's the mistake? I rushed. I wanted to finish in time. One more thing that I wanted to do. I should leave that. Rushing is not a good idea. What's the mistake I made? I didn't check U1.
TQ is greater than equal to U1.
Exactly. I didn't check that part. I checked it, so it said, assume that that's the case. Okay. And then I just directly jumped to the expected payoffs of player 2. Actually, I should have started with the expected payoffs of player 1. So if that's the case, we should have U1 of TQ greater or equal to U1 of BQ. Sometimes mistakes teach more than correct answers. Okay? So if T is in the support, B is not, then we have this condition. So I forgot to write this. I should also write this, which your friend noticed. So that says 2 QL plus 0 QM, I'm not going to write that, times 1 QR is greater or equal to, 3 QL plus 1 QM. Okay? I forgot this part. I rushed, and it's not a good idea. So again, I'll try to write everything in terms of QM. 1 minus QL minus QM greater or equal to 3 plus QM. So what do we have there? So 1 plus QL minus, so let's keep this 1 here. 2 QL plus 2 QM. So that implies I shouldn't have raised what we had before. QL plus QM less than 1 over 2. Okay? So that's what we have. Okay? Now I should go in and look at player 2's condition. Yeah. So, again, for player 2, you go step by step. Everything is in the support. Well, that's the part that I did in a rush, but that's the correct part. Everything cannot be in the support if player 1 plays T with probability 1. Only M and R could be in the support. Okay. Okay? Is that clear? Or should I write it? So if that's the case, we need to have U2 of TQ equal to U2 of TM equal to U2 of TR. But this is equal to 2, and this is equal to 0. They cannot be equal. So everything cannot be in the support. Okay? So support of Q is equal to M R. Okay? In that case, U2 of TQ is less than or equal to U2 of TM, which is equal to U2 of TR, because they're both in the support. So this was equal to 2, that's equal to 3, that's equal to 3. The conditions hold. Okay? So far, so good? So what do we have? We have QT equal to 0 and QM plus QR equal to 1. And we also had QL plus QM. That's not T, that's L. We also had QL plus QM less than or equal to 1 over 2, which means QM less than or equal to 1 over 2, and QR greater or equal to 1 over 2. But we assume that they're both in the support, so QM greater than 0. Okay? Okay? So the Nash equilibrium we get from these is PT1, PB0, QL0, QM, a positive number less than or equal to 1 over 2, QR, a number greater or equal to 1 over 2. And they sum up to 1. Okay? But then it keeps going. So you look at M is the only element in the support. Okay. Okay.
We have QM plus QL less than 1 over 2.
Exactly. So if M is the only element in the support, it has to have probability 1. As your friend said, that can't be the case. So then we look at, what was it here? R is the only element in the support. But that's, we already have found that as a Nash solution. So we don't have to worry about that. Okay? So then we go when PB is equal to 1 and PT is equal to 0 and repeat the same thing. Okay? So the bad thing about this, you see, the nice thing about this theorem is you have a bunch of linear inequalities, and you solve for them. So solving them doesn't require any high-level mathematics. Okay? Simple linear equations with inequalities in them, you try to solve them. The problem is there are too many cases to consider. Okay? Even with this 2 by 3, we had quite a number of cases to consider. Okay? And as the strategy sets increases, the number of cases increases quite rapidly. Okay? So actually, in this case, if we checked everything, for player 2, the number of cases we should consider is 2 to the power 2 minus 1. At least something should be in the support, right? And the number of cases that we should consider for player 2 is 2 to the power 3 minus 1, which is not much fun. Of course, as you work, some of the cases are eliminated. When we started, we noticed that, for example, here, when we noticed that QL plus QM is less than 1 over 2, we noticed that QM cannot be equal to 1. So the case where R is the only element in the support, we don't really have to check for it. Okay? But you might have to end up checking this many cases, which is not much fun. But the calculations are trivial. Okay? Any questions? Well, so today we don't have time. Next lecture, we will look at methods in eliminating some of the strategies. So we will discover conditions under which some of the strategies, pure strategies, cannot be played with positive probability at any Nash equilibria. Okay? But again, those will not be big eliminations. There will still be quite a number of cases to consider. So my recommendation is, if the game is 2 by 2, 2 by 3, 3 by 2, graphics becomes very powerful. Okay? You can see all the cases in a very summary. When it's big, then drawing those pictures becomes impossible. Well, for me, for most of us, for William, he does draw them somehow, my PhD supervisor. Okay? But in general, when it's 3 by 3 or larger, it's very hard to use pictures. You have to use these. In those cases, again, what we would do is look at the elimination possibilities, which we'll discuss next lecture after the spring break. That's it. Have fun. Have a nice break.